Korea.
Thank you very much, Anand, for this very kind introduction. It is my pleasure to be here sharing this talk with a lot of colleagues. So good morning, good afternoon, or good night where you are. I am very pleased to be invited for this lecture. The topic of my lecture is the impact of Internet of Things and LIDAR and the AI technologies on transportation geotechnics. Let me just let you know where I am and in which institution. So I am, as you know, in Portugal at the University of Minho. This institution has 1,737 lecturers and researchers, 12 schools and institutes that you can see, 31 research units, 1,722 PhD students, 21,000 students, and is an institution part of Arcus European University Alliance with 2,300 foreign students. I belong to the School of Engineering that has 9 departments covering the majority of areas in engineering, offering first and second cycle courses as well as third cycle courses together with research centers, and supports the development of research projects and knowledge transfer projects in cooperation with industry and service. It has also research units that covers a lot of research topics that you can see here, and I belong to ISIS. This is the Institute for Sustainability and Innovation in Structural Engineering. It was founding in 2007 to address structural and functional performance of built environment. Is a research center of a joint venture of 2 universities, the University of Coimbra and the University of Minho, and is rated, this research center, in the last 3 evaluation exercises provided for foreigners experts and promoted by our Foundation for Science and Technology, including the next period for 2025-2029. ISIS is the only national civil engineer research development unit formally integrating an associate laboratory, ARISE. It has 4 research groups, as you can see here, in green, with 11 research clusters, and I belong to the civil infrastructure cluster, and all the research unit integrate 78 research integrated members. You can see more detail in the link provided below. Let's move now to my talk of today. I will start with the background introduction to this topic. Then, as an academic, I will give some highlights concerning the Internet of Things, the artificial intelligence, and the Internet of Things with artificial intelligence, and their applications to earthworks, jet grouting for ground improvement, slope management, long-term track performance, and I will conclude with some final remarks. Let me just give you an overall view of the involvement that I have been in this digital era since 2010, and involved in a lot of associations and institutions and cooperative work. I would like to mention the FEDIX, mainly the Joint Technical Committee 2, representation of geoengineering data in electronic forms. I was pleased to organize the third international conference in Guimarães that was published in 2019. The topic was information technology in geoengineering, and then also the new created technical committee of the International Society of Soil Mechanics and Geotechnical Engineer, and these four theses are all in a certain way involved with the digital era. Then you have, of course, the TRB, and we have the recent created International Society for Intelligent Construction. You have here the link to see more detail about this international society, and I was also proud to organize the third international conference of this international society, Trends on Construction in the Digital Area in 2022, and also participating in a series of books that are being appearing, being the first one, Introduction to Intelligent Construction Technology of Transportation Infrastructure, that was already published in October 2022. It was also, I would like also to mention mainly the participation in the 75th anniversary of the journal Geotechnics in the topic of artificial intelligence in geotechnics, current challenge and future opportunities in research and industry, and also as a keynote speaker at the European Conference of Soil Mechanics and Geotechnical Engineering 2024 in Lisbon, with the topic how AI and IoT are transforming geotechnical site monitoring and construction, and the other lectures that were already mentioned in the introduction. I must say that, as I mentioned, I was involved with 15 years ago, starting interested in this topic of artificial intelligence, and the first publication really devoted to transportation geotechnics was published in 2013 in the Geotechnical and Geological Engineering, and more recently in the Journal of Transportation Geotechnics. For those interested in this topic, there is a very nice collection of very good papers in a virtual special issue collected in 2024 related with artificial intelligence in transportation geotechnics. The background of all these digital tools are in fact integrating the Industry 4.0. If I will do the analogy, I can probably call it Geotechnic 4.0, sorry, with involving big data, Internet of Things, and artificial intelligence. And we are really going to the Industry 5.0, which reinforce the role of industry for the well-being of the society, putting research and innovation at the service of the transition to a sustainable, human-centric, and resilient European industry. Here you can see different tools of artificial intelligence. just for a background, you can see that there are different types of artificial intelligence, different components, and different tools, mainly machine learning, knowledge-based systems, and optimization, and computer vision, robotics, and natural language processing, and automated planning and scheduling. Some of these tools will be applied in the practical applications that I will present further on in my presentation. Another important development contributing for the smart railway infrastructure, I 4.0, is related with the project that I was involved with and sponsored by the European Commission, the called Shift to Rail program. And in this program, there was aim that it was to make the materials with self-sensing capacity in order to evaluate the health monitoring of the structure and consequently make decisions in the management of the structure. So the framework is basically in two approaches. One is using embedded sensors, and a lot of the work is presented nowadays related with this topic. And in the University of Minho, under my supervision, we develop self-sensing material that have the capacity to have piezo resistivity changes with mechanical or environmental changes. It allows then to identify degradation locations, degradation levels, consequently condition index, safety index, and reliability index. And this is really a material that was developed with a lot of experimental work. Unfortunately, it is not yet it has not had the possibility to be applied in a rail track, but this is already in plan, and I hope that this will be done. Let me now go to the introduction of some background related with the Internet of Things. The Internet of Things was firstly introduced in 1999, and with the idea of internet connected devices. Then in the 20th century, everyday objects could be connected to the internet to communicate and share data. Later on, with the technological advancements, particularly in the expansion of wireless communication and sensor technology, IoT grew into a vast ecosystem encompassing smart homes, wearable devices, and industrial applications. So the major developments and capabilities include the integration of physical and virtual objects, the popularization of sensors, wireless networks, and the explosion of cloud storage and big data. The key challenge and opportunities remain. Technical challenge including compatibility, interoperability, and security, ethical challenge such as privacy, and opportunities for upgrading and transforming industries for smart city infrastructures. The growth and acceptance of Internet of Things in various industries have been driven by potential for improving efficiency, productivity, and quality of life. If we go specifically for geotechnical engineering, IoT has revolutionized how data is collected, analyzed, and used for managed construction and infrastructure projects. The integration of the IoT with advanced analytics like machine learning and digital twins enhance the accuracy and the efficiency of geotechnical assessments, ensuring the safety and the longevity of geotechnical projects. As the components of this IoT, the first important thing is for the sensors, the converters of analog to digital that has a crucial role by digitalizing analog signals, further processing and analysis. Then is the transmission and consequently after the communication. And there are different types of these communications, some that are very used nowadays, like cellular-based communication, and of course 5G with the capacity for handling vast amounts of data transmitted, analyzed, and stored. These technologies are used based on specific needs like range, power consumption, data rate, and development environment in geotechnical engineering. Concerning the web monitoring platforms, there are several available in remote acquisition system and manual input of readings for conventional instruments. And this is delivery in general by specialized IoT companies, telecommunication providers, geotechnical engineering firms, and cloud service providers like Amazon that you know. And more details, it was presented in my keynote lecture in the European Conference of Soil Mechanics and Geotechnical Engineering in Lisbon that I mentioned before. Another remote sensor is the LIDAR and INSAR. These technologies are complementary. INSAR, called Interferometric Synthetic Aperture Radar, gives insight into dynamic surface changes, while LIDAR, light detection and ranging, delivers precise terrain and infrastructure models. Combining both enhances monitoring and analysis for transportation geotechnics and hazard management. In the right side, you have the schema how INSAR works, and the main advantage of this remote sensing is the high spatial resolution, a wide area coverage, repeatability, non-invasive, and cost-effective. The ideal to have not just data acquisition and transmission is to have predictive capacities, and then it becomes the combination of IoT and AI. With this, starting with the artificial intelligence, this technology, as you can see, is much older than the IoT. It was mainly based in mathematical logic. It starts in 1950s, and after a lot of intelligent tools were developed, like machine learning, deep learning, ImageNet competition, and many others. The last decade, a variety of these technologies have been integrated with artificial intelligence. Just to mention some that are interested for us, mainly the Internet of Things that I already mentioned, but also quantum computing, augmented reality, and blockchain. The capabilities and the challenge when we have IoT AI is that, as mentioned it, AI research in the construction industry is mostly focused on the development and implementation of various mathematical optimization techniques, formal logic, artificial neural networks, statistical methods, probabilistic methods, and economic methods, which are collectively referred to as architectural artificial intelligence. AI reduces the time spent on the repetitive tasks by using the big data analytics and improving the work process. And with AI and machine learning, large data sets can be analyzed in a fraction of time, and algorithms can identify useful insights, categorizing, predicting, and making evidence-based decisions in novel ways, which will promote the growth of novel application and fuel the sustainable booming of AI. And I will show you later how this is reality in our field. AI has the ability to analyze remote sensors, as I will present also to you later on, with advanced sensors capturing image from the Earth's surface, providing valuable information about, in this case, geotechnical features. Autonomous robots and drones equipped with AI power sensors can be used to conduct remote site investigations, reducing the need for human interventions, mainly in hazardous or difficult to reach locations. AI algorithms quickly identify geological formations, detect changes in the land cover, and predict natural disasters like landslides. AI supports the design of more resilient and robust infrastructure projects. The biggest challenge to incorporate AI on the construction site is the fragmentation nature of the industry with different players, which has resulted in issues of data acquisition and retention. Let's now move to some practical examples. And I will start with the earthworks. As you know, the earthworks is one of the geotechnical works that is really very fitting with these tasks repetitive that we need to optimize. And in this case, the artificial intelligence techniques can really do the optimization of the mechanical equipment used in these tasks and providing the productivity of the work of earthworks. So we start from equipment in the excavation, then we have the transport, and we have the embankments. And this is a cycle work with different fronts of work during the project, mainly in the linear projects of roads and railways, where you have to optimize the equipment that you have in each front in order to produce the proper productivity in terms of the construction, embankment construction, in time and fitting with the costs. And based in this concept, and the fact that nowadays all the equipments, from the excavation to the transportation to the spreading, grading, and the compaction, are equipped with sensors and using the Internet of Things, is this possible to really change completely the work done general by very experienced people with these new advanced tools using IoT and artificial intelligence. So an optimization system was paired with an IoT system for earthwork projects. This was developed in Built Collab by one of my PhD students, Manuel Parente, and it has been divided in two parts. One that optimize according the design phase the time to do the work and the costs to did this work. And during the construction phase, we can see if what it was planned during the design phase fits or not with the construction, and if it is not fitted, the equipment is reallocated in different fronts in order to be always optimizing the productivity and the costs of the system. This is how it works, so we can have a kind of digital twin during the construction of the earthworks. Here, we have applied this, even if it is in a simulated way, to a case study involving 5 embankments fronts supplied by 4 excavation fronts with associated material processing volume ranging from approximately 5,000 cubic meters to 15,000 cubic meters. The original duration of the works correspond to approximately 3 weeks of activity, and the available resources to execute these construction projects were 5 rollers, 8 bulldozers, 12 excavators, and 22 trucks, with some variability in the models and consequently in the productivities as well. So the system itself, when you have, for instance, a contract with a certain kind of the equipment available, the system is able to use and optimize this equipment in order to give you an output of the production of this equipment, and of course the associated costs. If you have, for instance, a time imposed, in that case, the system can give you and optimize the best equipments that can realize this work in the prefixed time with a certain costs. And this is how the system really can answer to the questions. Here you have the output, just a 2D, but it can be also represented in 3D, between the costs associated with the duration of the construction for different possibilities, and you can choose the one that corresponds to the best option related with the project that you are looking for. Once you choose this option, you are able later on during the construction phase to check or re-optimize the system if you find some deviations comparing with the initial solution. So the system is all the time updating the solutions to give you the optimization in the field. Here you can exactly have the information about the remaining and the completed tasks, and if there is delayed to what it was planned, or if it is over or under budget concerning the situation of the work. To support these results in more detail, you have here some publications. You can see that the first was this one that I already mentioned in 2013, and then another in 2015, and more recently one in 2022, exactly focus in what I present here, that is a digital twin optimization framework for earthworks production optimization and management. Talking about earthworks, there is the compaction, and I didn't resist, even if the time is very limited, to talk a little about the intelligent compaction. As mentioned before, nowadays the compactors are equipped with different kind of sensors, giving the position, the interaction between the roller and the ground, and the data collection, as well as after the map. In fact, we can have in the roller equipment appropriated intelligent compaction sensors, GPS unit, real-time monitor, and data storage and transmission. Then you have the vendor software monitoring IC activity and converting IC data to appropriated formats in real time, and a geospatial-enabled software that is able to generate maps in real time to identify areas of concern, report the number of passes, locate areas with lower than anticipated stiffness, conduct statistical analysis for quality control, and the training personnel, that is an important task, collecting data properly, analyze results rapidly, and interpret quality of the work promptly. And this is really in the framework of the things that is being done in the International Society of Intelligent Compaction. Here you have a map of the output of this information with different colors, identify different stiffness or different degrees of compactions. And with this, you can elect candidates points for spot tests to identify and confirm the geotechnical parameters. The big challenge that we have nowadays is the use of the artificial intelligence in order to make the rover intelligent. And from the interaction between the roller and the ground, it is possible to adjust the parameters of vibration frequency, eccentricity block, eccentric distance, and rolling speed in order to achieve the parameters, the targets that are specified for the compaction. This is really nowadays very important. In fact, we have two approaches in terms of terminology. In general, we call intelligent compaction mainly in the United States, even if the roller is not intelligent. It just captures the continuous compaction control during the compaction with the parameters that are important for the quality control of the work. In Europe, the intelligent compaction was understanding with the possibility of the roller to have the parameters adjustment that I just mentioned, in order that it will react to the ground. For instance, if you have a soft ground, the roller will have a bigger amplitude. If you have a stiff, it can change the amplitude and increase the frequency. So this was the terminology used, but in European, when you have just the continuous control compaction, it is not an intelligent compaction. So there is some difference, and sometimes this can be misleading between communication of the people. Here you have a picture showing you how the things can work nowadays, like a train with all the equipment that provide the material until the final product has been done, and all the equipments are communicating between them and reacting to this communication. What is nowadays the big challenge is that there are the development of the compaction, that the compactors that have the intelligent compaction, but they can also be autonomous in the way like the cars, where they drive itself and they provide the adjustment during the compaction without human directly involved. And the same is possible with the excavators and of course the trucks. This is, as you can imagine, and a lot of this technology has been developed in war conditions, where people should not be, to open trenches cannot be there. So if you have these equipments with this automatism, this is a big challenge, and it comes also for our geotechnical works, and this will appear more and more in the future, I believe. Let's move to another very important topic in transportation geotechnics, that is the jet grouting for ground improvement. This, as most of you know, jet grouting technology is related with a large set of data variables involving soil properties, type of cement, injection pressure, nodal diameters, and so on. High-dimensional and non-trivial modeling task in this case. And using the predictive analytics by artificial intelligence, the aim is to model these nonlinear relationships between jet grouting input variables and the target variables. Generally, the target variables are the strength, the stiffness, and the column diameter. In order to evaluate the solutions, it is important to understand the jet grouting mixtures using a sensitivity analysis after we get the output of these predictions. And for this purpose, we have used machine learning algorithms like artificial neural networks, support vector machines, functional networks, and multi-progressions. From this, we have introduced 18 variables that involves the time or the age of the jet grouting, the volumetric content of the cement, the relationship between water and cement, the type of cement, the relationship between the porosity and the volumetric of the cement, the percentage of sand, the percentage of silt, percentage of clay, percentage of organic matter. The jet grouting system uses the inverse of dry density, the void ratio, the water content, the speed of the rod, diameter nozzles, the flow rate, the grout pressure, and the dynamic impact of the grout. So these are the main variables that can affect the target variables, and all this data is generally available in the field. So we have the possibility in cooperation with a contract to have data from jet columns, 632 records, 403 from field test columns, and 229 from project columns. And using these technologies, you can see how the prediction capacities we can achieve. In terms, I didn't mention here the strength because it was the more easy and is the more conventional. I choose the stiffness because it's a more difficult parameter. And in this case, in the laboratory, the measurements of the stiffness were done with the local measurements of the strain of the specimens, as it must be for this kind of material. And you can see the very good predictions obtained in this case with sport vector machines, compared with other algorithms that we have used. The best, of course, are those mixture formulated in laboratory, but you can see that in the field is still quite reasonable for engineering purpose, the prediction that we could achieve. And the best prediction was, and very surprising, by the way, it was the prediction of the column diameter of the samples. Anyway, for all this prediction is always important to check the interpretability of the results. And I just mentioned here the one related with the column diameter, because it was the one that gives us really a very high prediction. And you can see that the parameters that influence the diameter of the column of jet groutings, the main parameters, I will say even in the sport vector machine and artificial neural network, and I'm talking about the field, is the percentage of the sand, the percentage of the clay, the speed of the jet, and the pressure of the jet also. So this is what empirically we know that is important, and we can believe really in the results obtained with these intelligent algorithms. So some publications that has been done related with this topic. If you want to have more information, you have here the publication journals that has been used. Now let's go to the slope management. This has been done in two different steps. One, with the goal to predict the earthwork hazard category of the slope based in 4 risk classes. A, serviceable, B, marginal, C, poor, and D, too poor. This was done based in slope data kindly made available by the UK Network Rail, incorporating a lot of data, slope geometry, existence of trees, animal activities, ground cover, number of dangerous trees, and so on. And this for different kind of slopes in rock cuttings, soil cuttings, and embankments. And you have here the earth hazard categories data that we have for these records. And then we try to apply, I mean, we have tried different intelligent algorithms, but the last that we have tried with quite a good success is the nominal classification strategy. Then also with the regression strategy was implemented. And because of the unbalanced sample, we use the smooth, and the results obtained with the artificial neural network is the one that you can see here. And we have a superior performance in the prediction for class A and B. Of course, in all the type of slopes, in rock cuttings, in soil cuttings, and also in embankments, you can see that is a very good prediction. And also for the class B, as you can see here. However, for the classes D, the prediction is much less, mainly in the rock cuttings, but at least we can say that when a slope class is not correctly identified, for instance here, it is categorized as belonging to the closest class. In that case, the other one, that is the C. And for soils, these were much better, as you can see, for the embankments and also for the soil cutting. So this was really a very interesting achievement in slope management based in this data that I mentioned before. In conclusion, we could say that a new attempt was made by combining artificial neural networks and genetic algorithms for futures selection purpose. Although the overall performance has not improved significantly, the new models present some important advantage. They can achieve the same overall performance as machine learning by considering around half of the input variables. Higher performance is achieved, as I mentioned, on classes which represent the high probability of failure, what is the more difficult, of course, class C and D. And this study underlines one more the high complexity involved in slope stabilities. Some of the publications to go to more detail, and the last tentative is to apply the remote sensing techniques in order to predict slope movements and consequently hazards with slopes. In this case, we have for a network explore a data set and doing the following. A 5-moving window technique was employed to transform it into a new data set, training what it is, the training data set. This curated data set is more manageable for analysis and serve as the foundation for model training. We experiment different strategies to approach the prediction of slope movement and displacement. And for this purpose, we use the artificial neural network with one run configuration, around 80% training split and 20% testing split, and multi-regression cross-validation approach with a k-fold of 5 with 5 runs. And it was really very interesting to see that if we use the 4 passage of the satellite data to predict the next one, we have quite a good results. Even it was shown that if we use only 2 data before, it is possible to predict the next one with quite a good accuracy. And to finish, I will apply the machine algorithms for long-term track performance. The methodology that we have used for predict the permanent deformation in rail tracks, that, as you know, is the main maintenance problem that we have if you have permanent deformation in the rail track. We have developed a methodology where a finite element-based knowledge database was developed based in a validated finite element model 2.5D, and from this model we could calculate the stresses, and with the stresses using an empirical model we can calculate the permanent deformation for its passage, and then we can accumulate it for the number of passage that the loading is applied. And we have tried different machine learning models like multivariable regression trees, random forest, artificial neural network, and sport vector machine, using the input parameters adopted in the numerical modeling, as I mentioned, as inputs, and extract predict the permanent deformation response as an output. So in this case, I can say that this database have a short-term performance related with the passage where we calculate the stress and the resilient strains, and long-term performance where we can calculate the permanent deformation. This is the empirical model that we have used to calculate the permanent deformation for a certain number of passage, and you can see that he has only three parameters: epsilon, p0, b, and a. Is consequently a very simple parameter, and for these machine learning models we have the evaluation metrics that quantify the quality of the models, and you can see that it was by this sensitivity analysis that we have done, it was possible to really have an explanatory variables of random forest model with select variables showing that the cohesion, the speed, the P max, the mean normal stress, the maximum mean normal stress, and the constant of the parameters and the number of cycles were the more relevant for the predicted of the permanent deformation for the type of the track that we are analyzing. And as you can see, this was really a very good prediction. And in order to apply this to a real case in the field, I think this is quite unique. We have this possibility to have the data from a Swedish heavy oil line giving us data from permanent deformation obtaining during 11 months. And for this purpose, knowing the geometry and the properties of the materials, we could develop a 3D model. And with this 3D model, we calculated the stresses, and calculating the stresses based in the algorithm that we have tested before, we could predict the permanent deformation. And here you have the results. Of course, the red line here is the results of the random forest model that you can see that anyway is not a perfect match, but is quite a good prediction of unknown behavior of the field. So this is what we could predict without knowing the field results. So we were very happy and satisfied with these results. My final remarks. I'm sorry because I think I am quite long in this talk. I will say that artificial intelligence and IoT sensors provide real-time data for structural health monitoring and geohazard detection. AI-driven digital twins and machine learning optimized construction, earthworks, and performance simulation for infrastructure resilience. The study showcases the effectiveness of intelligent algorithms in earthwork optimization, predicting jet grouting mechanical and geometric parameters, as well as slope movements and long-term rail track performance. AI-powered robotic compactors can navigate construction sites autonomously. Computer vision and LiDAR helps detect obstacles, adjust passes, and avoid accidents. By enabling changing detections through repeated scans, INSAR supports forcing evaluations and ongoing monitoring, helping identify slope failures and assess the effectiveness of remediation efforts in real time. AI-powered IoT networks and large language models enhance infrastructure lifespan through predictive maintenance, automated reporting, and efficient resource management. The best practices involve integrating AI-powered systems that can collect vast amounts of data in real time and analyze it to provide actionable insights. By analyzing trends and correlation in the data, AI models can forecast potential incidents and trigger ear warning systems, allowing for proactive intervention and risk mitigation measures. As I show you, ensuring interpretability or sensibility analysis is very important in order to gain trust and acceptance of these artificial intelligence methods. In this case, the collaboration among all the actors is very important in order to unlock new insights and solutions to complex geotechnical and geological challenges. The couple of IoT and AI technologies present a parallel prospect for transforming transportation infrastructure, construction, and management methodology. This synergy heralds the era of safer and more resilient project and construction developments, delivering substantial advantage for all the players across the design, construction, and maintenance sectors. These three last sentences for me are really very important. Sharing information, digital exchanges between different actors and society, going for the, as I mentioned, the Industry 5.0 is a key issue that needs robust regulations promoting responsible AI practices, investing in education and training. Bringing together research centers, industry, and the users in a collaborative environment is a way to contribute for a more safe, resilient, and sustainable built environment of the future. And the last is what I am really encouraging very much, is that digitalization is an area to promote what we call the open science, that in my view is a route to follow. And I will say that the big issue is to achieve AI technology that continues to evolve, supervise large language models together will play a central role in shaping the next generation of intelligent, adaptive, and resilient geotechnical engineer solution, in particular in transportation geotechnics. And I will conclude with the thanks to a lot of institutions and people that help in all these findings that I present to you. And we are working in a book that will be I hope, available in around 3 months, because it's a little delayed. And some of these tools that I present will be inside this book. And it has also the cooperation of Anand Popala in a chapter giving the perspective from United States. With this, if you have some questions, as was being said, I will be pleased to answer them. And thank you very much for your attention and for excusing me for my speech that was a little too much long. Thank you very much.
Thank you so much, Professor Antonio Correa. This is really a wonderful talk, a technology-driven topic. So I just want to say thank you on behalf of NCIT, which is National Center for Infrastructure Transformation. I just have a few questions, but I think one of the questions I'll ask you, and then rest we will share with you later. Okay. The one question is, how can LiDAR data be effectively integrated with traditional sensors to improve accuracy and reliability?
Repeat, Anand, please.
The question is, how do you integrate LiDAR's data with traditional sensing methods to improve the accuracy and reliability of predictions?
Yeah, this is a good question. In this work that is doing at my university, there is a team of experts that is responsible to provide us this data from the remote sensings. So we are just working with this data that is provided by these expert people in analyzing and filtering this data in order that we can be trusting in this data for the intelligent algorithms.
Thank you, Antonio. I really appreciate your time. And I know it's very late in the evening, and we really thank you for that. And I will send it to Elisa. Elisa, want to close it as a closing mark?
Yes, I want to thank everybody for attending today's webinar series, and a big thank you to our presenter for a very insightful geotechnological, presentation today. And if you have any questions, please email me your questions and I can have a Q&A posted on our website. This webinar series is recorded and you can watch it at a later time, and all the questions and answers will be posted as well. Again, thank you all for coming in and sitting in with our presenter today. Thank you very much.
Thank you, Professor Correa, again. Thank you
so very much all for attending this webinar.
Thank you.
Lisa, how many people were attending? You are muted.
We had 108 people, Professor.
Wow.
Yeah.
Wow.
Let me go ahead and just get out. There's a few more stragglers here. 1 second. Let's have remove. There we go. Yes, so we had 108. Dr. Tooley is still on. I'm going to go ahead and for meeting. There we go. Okay, so now it's just us. So we had a total of 100. Our peak attendance was 108 participants. So that is amazing to have after a holiday weekend here in the States, to have 108 people attend. So congratulations. This brought in a lot of attention. It was a great presentation. This is one for the books for sure. Actually, let me go ahead and stop recording. This way, then none of this is on our, we'll just have it. There we go. And then I can also